a little bit about the projectiles. Huh? Yeah, I took that one. Yeah, right out of it. Okay. All right. So yeah, by Newton's second law of motion, we know that force equals mass times acceleration. Pretty famous little law right there. Okay. Well, the vector version, of course, the force vector would equal the mass times the acceleration vector. All right. So let's apply that to our projectile motion. All right. So we've got initial velocity vector. We know the initial velocity vector. We're going to use that. Going to be v0, that vector. And then we're also going to be provided the angle of elevation, alpha. Okay, so we've got our velocity vector here, and then our angle of elevation, alpha here. And so as we know, the graph comes out to be parabolic. And so let's see if we can come up with some formulas based on that information, that given information. All right, well, one other thing they label here for future reference is this is going to be distance d, which we'll find here in a second. All right. So we know something a little bit about this. We're just firing it with a certain initial velocity, and so the force we know acting on this would be gravity, right? Which is going to act downward on the way we've drawn it here. So we've got the force is equal to the mass times the acceleration vector. All right, and so we know that, yeah, our force is going to be downward. And so that means negative. And the acceleration, the only thing really acting on this is the gravity. So as far as the vector there is concerned, that's just a j vector, right? Which would be the gravity constant times the j vector, because all of it's directed downward. That's our gravity constant. And so out of that we get that the acceleration, get rid of the m's, right, is negative gravity constant times times the j vector. And we are going to use the meters per second squared magnitude of g here. So the magnitude of meters per second squared. Yeah, the magnitude of A would just be the gravity constant, which is 9.8 meters per second squared. Okay? All right. Now, what we can generate out of this then, of course, is velocity and ultimately position out of this, doing the same thing we just did in the previous example, since we know that the acceleration vector is the derivative of the velocity vector. The velocity vector is the integral of acceleration vector, which we've got. So the velocity vector then would turn out to be, well, we're just doing the integral of that, so it's just negative GTJ plus a constant vector. But we know we've got the initial velocity vector here. We called it V0. So V, this in terminology we're using here, that is V0. And so that is going to be, yeah, so that's going to be, what's the constant vector going to be? It's the initial velocity vector, yeah. V, so this is what we're saying. V of 0 is the velocity vector. Time equals 0. And so whatever that is, that's going to be our constant, because at V0, this is going to be 0. So we're going to have the constant equals V0, which we know is V sub 0. Okay. A little confusing, I guess, notation-wise. But so that's going to be C also. So V of t is negative GTJ plus our velocity initial vector. Okay? All right, now, that gets us our velocity vector. What about our position vector? Well, if we integrate again, integrating again, that'll give us R of t. Since V of t is equal to derivative of R of t. If we integrate V of t, that gives us R of t. So R of t here is going to be the integral of V of t, which that's going to be the integral of negative GTJ plus V0 vector t. So what does that give us? Negative 1/2 GT squared. You may have seen that before. Just comes from a little bit of calculus here. Plus the integral of that would just be V0t. Yeah, V sub 0t. Because we're integrating with respect to t. Yep. It's just a constant vector. And then plus our constant vector for that integral. Now, good news is on that one is what's our initial position vector? Well, we're starting at 0, 0, 0, or 0, 0. So D, so R of 0, the initial is just 0. And so that's D. So yeah, that one just goes to 0. So R of t is negative 1/2 GT squared plus V0 t. All right, now they go a little bit further with it to kind of get some parametric notations for our x and y values. So let's talk about that. Okay, so our initial velocity vector is v0, and so the magnitude of v0, get rid of some of this, they're just going to let be v sub 0, so v sub 0, just a number, is instead of a vector, that's just the magnitude, the speed at which you fire the projectile initially. All right, so let that be v0, the magnitude of the velocity vector. Then we can write the velocity vector in terms of x and y here, and ultimately v sub 0. V sub 0 here is just going to be whatever the x value is. I call it x0, I, plus y0, j. But if v0 is our initial magnitude of this thing, then what is x sub 0? Yeah, so it'd be v0 times the magnitude times cosine of alpha. Yeah. Because we've got the cosine of alpha, then would be x sub 0 over the magnitude of your velocity vector, right? That's where that's coming from. So x sub 0 is v0 cosine of alpha. And then similarly, the y component then would be the sine, right? v0 sine of alpha, same idea. Okay? All right, so that makes then, if we make that substitution for v0, the vector down here, let's write r of t then. So I'm just going to plug this in for the v0 right here. So that makes r of t negative 1/2 gt squared plus this, v0 cosine of alpha I plus v0 sine of alpha j times t. Let's see, I forgot. I forgot down here. Yeah, I forgot my j right here when I was writing my r of t vector. R of t is, so this should be j. There's a j here. Yeah, forgot that. Maybe there's something missing there. Yeah, so combine the well, I've got two j vectors here represented and only one I, so r of t, turns out it's v0 cosine alpha times t I it's the I component, plus then the j component. Well, you have this as part of the j component and then this times t, so I think they usually write it v sub 0 sine of alpha times t minus 1/2 gt squared. Isn't that the way they write it? Okay. All right. Okay. And so parametric equations of the trajectory then, so that would give us the position, so they just then split that out, the parametric equations of trajectory of this projectile motion based on this. The x is this, v0 cosine alpha times t. And then the y is this, v0 sine of alpha times t minus 1/2 gt squared. Okay? Okay. All right. Yeah. Well, we're going to find, first of all here, the distance it travels. Do the distance travel. And just kind of get us started here. D, this D right here, what do we know about that? Well, the D would be when the y component is 0, right? The distance D is the x value when y is 0. And this y equals 0, not that y equals 0, because notice here, if we let the y component be 0, then we have v0 sine of alpha t minus 1/2 gt squared, which you can factor off a t, which that'll give us t equals 0, right? That's not the one we want. But then we have sine of alpha minus 1/2 gt. So t equals 0, that's not the one we want. We want when the sine of alpha minus 1/2 gt equals 0. So t, if you solve that for t, yeah, you get sine of alpha over 1/2 g, which is 2 the sine of alpha over g, right? So it's going to be that time right there, but you don't have to necessarily remember that. But an interesting thing, if we do go ahead and plug that in for x here, so the x component then, so the d would be then the x component at this time t, so that'd be v0 cosine of alpha times the t, which is 2 sine alpha times g. Okay. Squeeze that in here, maybe. If you combine the this right here, that is cosine alpha times 2. That's 2 sine alpha cosine of alpha. 2 sine alpha cosine. So that's a double angle, right? That's the sine double angle. So it's v0 times sine of the double angle 2 alpha over g. That's your maximum distance, or that's your distance that this thing travels. But like I said, you don't have to. Did I forget something? Oh, I forgot this. Yeah, I forgot the V0. I forgot the V0 here. I knew there was something I'd forgotten. Yes, so this will be times V0, so you got V0 squared here. Yeah, all right, so I think you got it. V0 squared, sine of double angle. All right. Okay. Okay. Yeah, so let's work through one of the problems here. Well, yeah, the maximum of sine is +1, right? So your sine of your double angle needs to be 1. Yeah. Okay. All right. So we've got a projectile being fired with initial velocity Okay, so let's do projectile fired, initial velocity 150 meters per second, angle of elevation is 45, which gives us the best, like you said, the best angle of elevation to get the maximum distance out of that thing. And we're going to fire it, in this case, from a position 10 meters above the ground level. So we'll have to do a little bit of adjusting. Where does the projectile hit? And with what speed? Okay, so in our notation here, what have we got? Initial velocity is 150. That's the V0, right? Just the magnitude of our velocity vector. The angle of elevation, so that's alpha, is 45, so let's call it pi over 4. And then, yeah, the adjustment we make, remember, our calculations were for the thing starting at 0, 0, but now we're starting 10 meters above. So yeah, we're just going to move the y value up by 10. Okay, so what we know is that the x is V0 times the cosine of alpha times t, so that would be 150 cosine of pi over 4 times t, so that would be cosine of pi over 4 square root of 2 over 2. Square root of 2 over 2, so that would be 75 square root of 2 t. All right, then the y is V0 times sine of pi over 4 minus 1/2 g t squared. Oh yeah, times t. There's a lot of variables and things to plug in. So now that, like I said, the x isn't affected by our moving it up 10. It's still x. But the y value, we need to move that up, so we need to add a plus 10 here. All right, so in this case, we've got 150 times sine of pi over 4 is also square root of 2 over 2, t, minus 1/2 g is 9.8 meters per second squared, and then t squared plus 10. Based on those formulas. Now, what were we looking for? We were looking for the distance that this thing travels. So a picture here. So I want that distance, which turns out is the x value of the thing when the y value is 0, projectile. And we have a quadratic, yes. All right, so yeah, we want y equals 0 to get this this x value, the y value is 0. So I'm going to set, yeah, let's just set that. Let's see, that goes down to 75. So set that, set the y value equal to 0. So that would be what, 4.9 t squared plus 75 square root of 2 t plus 10. We want that equal to 0. And so the t, the time, would be negative b plus or minus the square root of b squared minus 4ac over 2a. 9.8. Okay. All right, so you calculate that out. I don't have my calculator, so I'll rely upon yours just to see if I've got this all correct here. What answer do you get?
It's
21.74. Yeah, and is the other one negative? You get one positive, one negative? I think you might. I don't know.
they actually did
But I'm saying this gives us two answers. I was just wondering what the other one was.
Yeah, they didn't give us
Okay. Yeah. Oh, you didn't do it. All right. You're doing like me. You're using what the book got. Okay. All right. Okay. So anyway, there's another value here, but it apparently is negative. I don't have it worked out. So. All right. Yes. Yes, that is correct. It is negative because that one would be on this side, wouldn't it? All right. Now, what that gives us then is a way to find the x value, which that's what we want. The d then is the x value when y equals 0. And so that would be the 75 square root of 2. We found that the time is 2174, so plug those in, and you get approximately 2,306. That would be meters. So that's our distance the projectile hits.
2,295.9 for shooting it from the roof. So you're not equivalent. That's not a very high clip. But that's only a difference of 10 meters. It's funny how you shift yourself up 10 meters and down. It's pretty really small.
Yeah.
Your X.
Okay, yeah. All right, now, the other component to this was what was the speed that hits, and really the only thing we need out of that is the time. The time was 21, hits the ground at t was 21.74. Because our speed is going to be the magnitude of our velocity vector at that particular time. Right? So we just need to come up with the velocity vector. It's r prime of t, okay? So v of t is going to be r prime of t. And r prime we know was this from our calculations. It's v0 cosine of alpha times ti plus v0 sine of alpha times t minus 1/2 gt squared j. Whoops. It's RT. And so v prime then is going to be the derivative of that. So just be v0 cosine of alpha I plus v0 sine of alpha minus g minus gt j. Okay? So we know these things, right? v0 is 150 times the cosine of alpha, so that's square root of 2 over 2, so that's the I. Plus then v0, 150, sine of alpha, square root of 2 over 2 also. Look familiar? Minus 9.8 t. And so v0, so the magnitude be 75. So the magnitude would be 75 square root of 2 squared. That would be 75 square root of 2 minus 9.8 times the time when it hits the ground is 2174. So we'd multiply that. And then subtract that from the 75 square root of 2. And then square that. That would be our magnitude. And so that turns out approximately to be 151 meters per second. Do all that out. All right?